All right, ladies and gentlemen, thank you so much for joining us today. On behalf of AUVSI, I'm pleased to welcome you to today's webinar, Sensor Fusion Visualize for the Operator in a Complex Multi-Sensor World. My name is Keely Griffith, and I'm the Director of Industry Education here at AUVSI, and I have the privilege of being your host for today's webinar. Before we get started, I have a few housekeeping items to cover. As always, all participant lines are going to be muted during today's webinar, and a recording of the program is in progress, and a viewing link is going to be emailed to all attendees along with a copy of the slide deck within the next week. You can also now view all of our webinars on AUVSI's new learning and engagement platform, Able, which I'm really excited about, and it makes the registration process that much easier. If you're listening to the broadcast and you need assistance, please send a note to the webinar leader using the chat at the bottom of your screen. Please note that any of the links featured in the slides will be shared through the chat during the presentation so that you can click on those and access later. After the presentation, we're going to open the session for Q&A. Attendees, you're encouraged to submit questions at any time throughout the webinar using the Q&A button at the bottom of your screen, but questions will only be answered at the end of the presentation. Please note, this is a different box than the chat, so please submit all content questions using the Q&A, which can be found next to the chat. All right, let's get started. So we'd very much like to welcome back and thank our sponsors, Kongsberg Geospatial, for their support today. And joining us from Kongsberg Geospatial is an excellent speaker, Paige Cutlin. Paige is currently Vice President of Sales and Marketing for Kongsberg Geospatial and joined the firm in August 2014. Paige has been in industry since retiring from the Canadian Air Force as a major in 2000. Paige flew on the Canadian CP-140 ASW aircraft as a tactical coordinator and mission crew commander. His last posting in the Air Force was to the Air Strategic Plans, formulating the initial Royal Canadian Air Force requirements for the Justice Strategic UAS capability. Paige joined industry in a project management role and has been directly involved in UAS program delivery and sales to various federal government departments for over 15 years. He's also a graduate of the University of Manitoba and the University of Ottawa. We're thrilled to have you today, Paige, so I'm going to turn it over to you and just let me know when we're ready for questions.
All right, thank you very much. What we're going to talk about today, and thank you everyone for joining us this afternoon, is a little bit about Kongsberg Geospatial. I'll talk about the IRIS Remote Operations Center, which is the application within which our sensor correlation service resides. We'll talk about the architecture and how we provide that correlation function to the operator, and then what it looks like through some example videos, and I'd be happy to take your questions. So Kongsberg Geospatial has been around for about 30 years. We're roughly a 50-person software company located in Ottawa, Canada. We're owned, perhaps obviously, by Kongsberg of Norway, and they bought us about 15 years ago. And what we're known for back in the day, and still to this day, is our TerraLens geospatial map engine. And that, going sort of clockwise here, is used by air traffic navigation service providers like Nav Canada uses TerraLens in all of their terminal and en route displays. It's used in the back of the Royal Australian Air Force Wedgetail and other Wedgetail clients, so that radar display in the back of the aircraft that's looking out over the horizon and seeing, thousands of tracks at once. TerraLens is used in the US Navy Air Traffic Management System. It's used in the control station for the Triton and NATO AGS Global Hawk systems, and it's used in the remote air traffic control tower programs by our parent in Norway. And the last use case is the NASAMS Fire Distribution Center. So think of that as the user interface for the NASAMS surface-to-air missile system. And that user interface is what we based IRIS upon. We took that NASAMS user interface software and we reused and repurposed it for commercial UAV applications. So it comes with that very strong background as a mission-critical real-time display system. So with that, we created our IRIS Remote Operations Center airspace visualization application. And the goal of IRIS is to really help in making decisions easier and safer. So you can look at this example of an air traffic controller and the umpteen displays in front of the operator there who has to, fuse all of this geospatial information and track information in their head to make a decision. So the goal of IRIS is to enable that decision making faster and safer. So IRIS basically has three elements. There's the integration framework layer. There's a services layer where we start to perform calculations and analysis on all of that information we've brought into IRIS. And then there's the user interface to present that information. Or to say it another way, as in words here, is that integration framework is the experience we have in integrating and aggregating all of that sensor, system, vehicle, and weather data from what could be very distant locations. So we did some tests recently using one of the telemetry tracking services. So we did a FlightNow test with drones operating in Norway and visualized in IRIS in our Ottawa office, and another test using the Elsight Halo system, and the drones were flying in Arizona, and we're able to visualize them in our office in Ottawa. So that sort of capability exists now to remote your operations to what could be a distant location, and that's what IRIS supports. The second aspect of IRIS is that the calculations that we perform on all of that data that's been brought into IRIS, and we provide what we call services. And one of those example services is detect and avoid, where based on understanding the proximity of a external track to your own ship, we can calculate and cue you as to detect and avoid. And finally, the third aspect to IRIS is that user interface. And I'll show you a video of the various tools and cues, alerts, and warnings that we can provide to the operator to provide that decision support that they need in a very complex environment. So as said, we are aggregating, fusing, and presenting information. So this is an example, sort of a hierarchy of, at the bottom, you see that data that's fairly static, such as terrain data or digital terrain elevation data, maps, satellite imagery. The next layer is data that gets updated periodically, like your aeronautical data of airspaces, aerodromes, and obstacles every 56 days. It gets updated in Canada, so that needs to be refreshed in your display to keep it up to date. Then there's live data that's coming into IRIS from what could be ADS-B or telemetry feeds or live weather or some of those tracking services. And then finally, there's your own ship information from your own single or fleet of drones that you may be managing. And with all of that information in IRIS, we can provide those services, like I said, which could be detect and avoid for the operator. So here's an example of a high-level architecture, and top left, you see the various types of data feeds that we can bring either directly into that DDS middleware layer, or we also have an API, a REST API or an MQTT interface that we could bring that information. And then DDS is a publish subscribe middleware that allows us to share that information around with the various services that we have there on the bottom left. And then within this network, we can then have multiple IRIS operators, which may be in the same office or may not be in the same office, but they can share that data amongst themselves. And as one enters information, it can be seen by another IRIS operator, or they can be segregated so that they're operating independently. And one of the services we provide is that ability to talk to the autopilot of the aircraft. So we have a telemetry service that can either allow us to just monitor the telemetry coming from the drone, or actually to mission plan and control the autopilot during the flight. And finally, on the right side there, we can interface to the internet. So that is typically the interface to a UTM provider, but also allows us to bring web-fed information such as weather or what it might be. And then we have an IRIS web viewer application that can allow your headquarters or other remote viewers to access via the web a picture of what's going on where your IRIS operators are using IRIS. So this long list, I won't go through each item, but you can see the different types of sensor and data feeds that we've brought in to Iris and various integrations for various clients. So there's various sensor types. There's telemetry services like FlightNow and the Elsight Halo, our recent integrations, RF detection systems, which is more on the counter UAS side, EOIR cameras. We've controlled sensors and cameras through Iris that in one case was on a tethered drone system. We were controlling the sensors through the Iris UI, different types of UTM feeds and live ATC feeds like the Harris Next Gen feed for the US or the Nav Canada feed for Canada. Here's an example of a project we did, which illustrates very well the different aspects of Iris. So it was a program for Defence Research Canada, where we had to first do a trial on a number of different counter UAS radar types. And then through the project, 4 different types of radar were integrated within Iris, along with ADS-B and along with ground and personnel trackers, and just to create a single operating picture for the Iris operator of everything that was going on in the local area. And then we're actually able to push that track picture to the Microsoft HoloLens. So as they scanned around the horizon, there would be a circle around where that drone might be coming from, as was picked up with the radar, and that you could see where it was coming before you could actually see the drone with the naked eye. Another example of a remote operations center is the Area EXO Autonomous Vehicle Test Range here in Ottawa. So again, similar theme of a variety of different types of sensors and vehicle trackers integrated in with other companies' systems, and we provide the visualization for the test range using Iris. So what I thought I'd do, I've talked a bit about data integration, is to show you a video of what the user interface of Iris looks like. So I'll play the video and just narrate it a little bit as we're going along. It's about a 2-minute video. So let me push start here. So Iris can be operated as a touchscreen, which is fine for sort of the coarse display controls, but I think a mouse or a trackball works better for some of the fine display selections. So you can see here the 2D and the 3D viewport that I'm manipulating. You can resize and reshape these and deselect them off of the display. You see what we call a deck of cards here, where any one of these views can be dragged into a viewport for the operator to see. Here's an example of a track list. You can pan, tilt, zoom. You see the track symbology there and the 3D viewport. These are different layers of information. You can see obstacles, airspaces. Here's some live weather in Iris. There's the track block with the parameters from that vehicle and the history length being adjusted there. This is more of the live weather feed. Here's an example of some very high resolution terrain and a warning from a loss of separation, a warning from a vehicle entering the geofence that you're in. A different view, that was the OpenStreetMap format. There's different GIS layers. And for each of these, you see the opacity bar you can control. Here's an example of loss of separation with terrain. Here's the very high resolution urban data being depicted. Here's the line of sight at real time being shown, the relative altitude of the local buildings being shown here. This is the Aireon space-based ADS-B that we've integrated being depicted. So a lot was covered there, but I just wanted to give you the example of what the user interface looks like of Iris. So the basic path of Iris as we evolve it is to reduce the cognitive load of that operator. And we have some of our clients who are trying to get to more than one drone being managed simultaneously by a single operator, which we can do and have done and demonstrated for the FAA. And so to enable that, we're providing more and more decision support for that operator. So to talk today about our sensor correlation service, the goal of our correlation service is to provide what we call a basic correlation. And I'll explain what I mean by that of the displayed tracks to minimize the screen clutter for the operator, because you could have a situation where that single UAS could be emitting ADS-B, it could have a telemetry tracker, it could have the on-chip telemetry to the control station, it could be being picked up by your own counter UAS radar. So you could have 3, 4, or 5 different tracks for a single aircraft, and what we provide is the ability to filter that down to a single track being displayed to the operator. And there's 2 main ways that we do it. The first is the sort of 3 degree of freedom correlation of we calculate a given sphere around the track that in the video you'll see is around 10 meters. And this is set by the operator. So you could have a very tight sphere or you could have a very generous sphere. And then in addition to that proximity, we also calculate which other tracks within that sphere have a similar course over ground. And again, that variation is set by the operator. And finally, we then also evaluate which of those other tracks on a similar course have a similar speed. And that again is configurable by the operator. And so in addition to that proximity and behavior evaluation, we also display based on the prioritization of the source. So there's an explanation here, but basically of that list of possible tracks that you could display from ADS-B to telemetry to a tracking source to a radar, you would choose the priority. So perhaps the ADS-B out is your priority. So we will also prioritize based on, as long as we have all of those, that would prioritize by ADS-B. As we get down to a lack of a self-identifying track and you're just into radar tracks, then we would revert automatically to that proximity and behavior way of filtering which tracks get displayed. So what I'm going to show here is a video, and what you're going to see is 2 different types of tracks. One is a track coming external from Iris, and then internal within Iris, we have a simulation track running as well. And what you're going to see the operator here is they're going to be turning on and off the visualization layer of the simulator. And basically what you'll see is that as the green track starts moving, you'll automatically see the pink track because they're no longer correlated, because the behavior of the green track is differing from the pink track. And then you'll see the operator, he's just going to turn on the simulation layer for a second so that you can visualize it. He's not turning it on and off per se, he's just turning on and off the visualization of that pink track to show you that it still exists. So it disappears when it's correlated. He'll show you that it's still there. He'll turn off the visualization of the simulation layer, and when it's not there, it's because it's correlated. And then it appears again when the green track starts moving because it falls out of correlation. So I'm not sure if I explained that well, but I'll explain as we go along. So you can see there's the 2 tracks. As the green track starts moving, then you'll see that the pink track reappears because they're no longer correlated. Then the green track is going to stop moving and the pink track will disappear because they become correlated. And then he's turn on the visualization, the simulation. You can see it's still there, turns it off again. So as that green track starts moving again, you'll see the pink track appear again because they're no longer correlated. And these are probably about, it looks like based on the legend in the bottom right, that these are probably about 7 or 8 meters apart. kind of range. So the green track is going to stop moving. The pink track will disappear because it'll become correlated with the green track based on it's within that sphere and similar behavior. Then he's going to start the green track moving again. You'll see the pink track appear because they're no longer correlated. So he's told the green track to stop. As it comes to a halt, the pink track will disappear because they're now correlated. He's shown us that it was still there in the background. Now it's correlated. He'll start up the green track again to move. And as it starts moving, you'll see the pink track reappear because it's fallen out of correlation. So once again, as that green track comes to a halt, the pink track will disappear because they become correlated. All right, I think you get the idea. So what's happening in this next video is you'll see a group of 5 tracks. And again, you'll see the mouse is, there's 2 layers in this video. There's the correlation engine, which is always running. And then occasionally the operator is going to reveal the simulation visualization layer just to show you that the tracks are all still there, but the correlator is running the whole time. So we see our gaggle of 5 tracks here. He turns the correlation on and it's down to a single correlated track. Then he's diverged the heading of one of the tracks so it falls out of correlation, and it's going to turn back on the same course and speed and fall back into correlation. He's just revealed the simulation layer. You can see all the tracks are still there. And now that one track is deviated again for heading, so it's fallen out of correlation. And it's no longer within the sphere of distance. You can see it's separating there. So it will remain uncorrelated because it's no longer meeting that operator set criteria for tracks that should be correlated. So in this case, it has the same heading, speed, and altitude, but the distance isn't close enough to say that it should be correlated into that main track from the group. All right, so this next video is going to show radar correlation. We've integrated with the Echodyne EchoGuard radars. So with that radar, it's typically about a 120 degree at max coverage from each radar face. So you normally use 4 radars to provide 360. And we have integrated with the EchoGuard to provide a correlation service for our customers so that where you have those areas of overlap, then we will only provide a single track as the vehicle passes between that overlap from one radar to another. So I'll just start the video here. You see a track appearing on the left side as it enters the radar coverage. The correlator is on, you can see in the top left there. And as it passes into an area where there should be 2 tracks, you can see it was briefly there. Now he's turning on the radar visualization. You can see the 2 tracks are being reported, but with just the correlator running, you're seeing that those 2 tracks have been correlated down to 1. And then just as it's passing here, I believe he's going to turn. So you saw the 1 track has now been dropped, and we're seeing the single track from the radar on the right. So this last video shows the correlation service we provide for the Iris Automation Cassia G sensor. And what you're seeing here is the 2D view on the left, the 3D view on the right. Those are the coverage areas, the expected coverage area from the Cassia G sensor. And you can watch as the track moves sort of across these different sensor coverage areas. So let me start the video. So the operator has just shown some of the amplifying information from one of the sensors. We have a track being there. Sorry, I think I accidentally restarted the video. Apologies. So the track's going to appear. And the one thing I just wanted to show here, I stopped the video, is what that Iris G sensor, Iris Automation Cassia G, I should say, sensor is passing is not only the track position, but it's passing as a screenshot of what the sensor is seeing. And we take that screenshot and we present it to the Cassia G operator through Iris so that they can help the sensor, because that might be obviously a bird or something other than a drone. So it's just an example of the data we're receiving from the Cassia G sensor that we're able to present at real time to the operator to help them understand what the Cassia G sensor has picked up. So I'll just keep the video going now. You see it's passing into the coverage of the second sensor. So both sensors are detecting it. A single track is presented to the operator. It passes out of the coverage of the first sensor into just the coverage of the second sensor, which is therefore indicated as red. Now we're in that overlap zone between the two sensors. We had a little cue there that came up at the bottom that one of the sensors was not operational. That was passed on to the operator. And you can see as it passes into that sort of dead zone between the two sensors that the track is dropped. And then as it keeps going, it's picked up again by the final sensor. So this is an example of how we visualize the correlation of tracks across multiple sensors of the Cassia G system, and as it crosses that overlap area between two Cassia G sensors. So as a summary of what we're doing across sensors is that we work across dissimilar sensor types. Some people call that fusion when it's a dissimilar sensor type that's being combined. We just still are calling this basic correlation. You can certainly earn a PhD in sensor fusion, and we're not trying to say we're doing that, but what we are doing, we think, is very effective at reducing the screen clutter for the operator by being able to reduce or filter down to a single track based on that proximity and behavior and the prioritization of the source. So with that, I'll just mention that we have some new features coming up in Iris. There's the suggestive avoidance service that might be the subject of our next webinar, where based on our conflict prediction service, or that loss of separation in the detect and avoid that we're providing, we provide visualization of suggested avoidance maneuvers for the operator. And as mentioned, we have the flight-based integration now, which we've tested with drones as far away as Norway from our Ottawa office. And finally, some high-resolution terrain sources that are new to Iris that we're integrating. So I think that's it for me. I thank you for your attention. I'm certainly happy to try to answer any questions. I apologize, but today I don't have an engineer supporting me. So if I can't give you what I think is a fair answer, then certainly your questions are recorded and we will provide them to our engineer, and we'll get back to you within a couple of days with a detailed answer to your question if I can't answer it myself today.
All right, perfect. So we are opening up the session to audience questions. As a reminder, you can submit a question using the Q&A feature at the bottom, right next to the chat. So just type your question and hit the submit button. It looks like we already have one page. So could you expand on your application of AI and machine learning to reduce operator workload?
Well, that's a great question, and it's such a nascent area of development for us. And what we've done in a couple of cases is to allow the AI to help in the route selection for the operator. So the ability to ascertain landing zones en route in a mission is one example. We've also applied machine learning to the sensor data that's coming down from the drone to detect moving targets within a video scene, as example, to recognize, basically getting that sort of automatic target recognition application is another example of how we've used ML. So there's a few examples. I suggest you reach out to us and we'd be happy to talk through in more detail what we're doing there.
Great, thank you. Another one. So are you and your customers interested in a true fusion solution? And what's the customer base for this type of grouping by proximity?
I'd say certainly we are. And the one thing I'd say is we're not trying to be an AI fusion company. That's not what we do. We're a visualization company. And we provide what I call that basic correlation service, which serves to declutter and present a single track to the operator. But we by no means are trying to solve the fusion problem. So if there's a customer or potential partner that has a fusion engine, then what we do offer is that integration framework background, that DDS that allows us to integrate with someone else's AI. So if I imagine there's a lot better ways of doing this perhaps, and if someone has a better way of doing or presenting that fused information, we'd certainly like to talk to them.
Could you share a little bit about customer use cases that you're working with right now?
Sure. So I mentioned a couple of the sensors we're working with. So the Echodyne EchoGuard radar is one where a customer had a 4 radar setup to provide 360, and they wanted that correlation of the track as it passed into that overlap zone between radars. They didn't want to see one track and then 2 tracks and then down to 1 track. So we provided the correlation service for them. I also talked about the iris automation. So again, similar situation where you can often have a number of the Cassia G sensors to cover off something like a city. So again, there'd be multiple areas of overlap where they don't want to see multiple tracks during the flight time through that overlap area. So that's another example of working with that sensor type. And then in general, a common use case for us is where there may be a telemetry tracking service plus telemetry plus ADS-B out from a drone, and they don't want to see all 3 tracks. So we use that prioritization schema to just display a single track, even though they may have multiple sources of position for that drone.
Great. There's a few other questions that have come in. How does the platform conform or need to conform to aviation standards such as DO 178 and DO 278?
So it's a good question. And it's an area where I'm not aware of a regulation like that as yet being imposed upon a ground control station, but I certainly expect that that will be the case. I doubt it would be 178 because that's typically for airborne cockpit displays, but I certainly believe it could be something like DO 278, that ground-based equivalent, typically for air traffic control applications. We're very familiar with 278 from our work with NAV Canada and with Avinor in Norway. So I do expect that that sort of design assurance approach, similar to 278, could definitely be called for, and it's something we're familiar with. But if that person is aware of that sort of software design assurance standard being imposed on a ground control station? I'd like to hear about it.
One more, how will the system recognize AC in distress to be able to give way in emergency, or if EMS AC is in the air?
Do you mind just reading that question again, please?
Sure. Here, I'm gonna also stick it into the chat because I think that'll be helpful for you. I know it would be for me. So how will the system recognize aircraft in distress to be able to give way in emergency, or if EMS aircraft is in the air?
Oh, I see. Okay. Yeah, I understand the use case. I think that, so sort of like a transponder being squawked that would change the way that you would treat an aircraft. I imagine we would visualize it, and I'm obviously making this up as I go along. I imagine that EMS aircraft or that aircraft in distress would be allowing us to identify them as such so that we could visualize them differently. So whether that's a transponder, or we would need some indication from them, some way of receiving information from them that they are of that category, and then we would visualize them differently in Iris to draw their situation or identification to the attention of the Iris operator. So that's always the case with Iris, where we're very strong and very lots of flexibility on the visualization side, but we need to get that data into Iris. So it's sort of, how would we be made aware that their EMS are in distress? And then if we were made aware, I'm sure there's a very obvious way we could make that apparent to the Iris operator. And if that didn't answer your question, then please contact us after. We'd be happy to talk about it.
All right, one more. Could Iris offer some of its services through an API?
It certainly can. We've integrated and created a REST API, and also for MQTT. So there's further extensions to that planned. If you have a specific way that you would either like to pass information to us or receive the information from us, then we'd be happy to talk about that.
I'll give everyone a minute to think about another question. And while we're waiting for that to come in, Paige, do you have any other thoughts that you want to leave with the group? I know that we already shared your contact information, so individuals will likely reach out after. There have been several comments to that effect. But do you have anything else while we're waiting for one more question?
No, I thank you. And I'd just like to emphasize again, I apologize our engineer couldn't be here with us today, or our second or third choice engineer for a variety of reasons conspired against us. So thank you for putting up with me as the sales guy. And if you'd like to have that more technical discussion, I entirely understand. And we'd be happy to do that. Just reach out to us and we'll set that up.
All right, I knew we'd get another one in. You just have to prompt a bit. Are there encounter scenarios, so relative speed, relative vertical rate, et cetera, where you think visualization is not sufficient and automation of the avoidance maneuver is needed?
Absolutely. And the way we're going with our suggestive avoidance is that when you set up your parameters for that warning that you would like, and the separation, that loss of separation, or what's the minimum that you would tolerate, it may give you, and we may be able to depict in our visualization that you have, let's say, 18 seconds to react. And you will see this kind of countdown effect of, if you don't make a decision in that amount of time, then you will have told us what your priority of actions to take will be. So basically, Iris is giving you the opportunity as the operator to be in the loop, and we'll show you visually how much time you have left to make a decision and what your suggestive avoidance maneuver is based on what you've told us you would like to do given this sort of situation. And if you don't make that decision, then the next logical step is for that automated response through Iris to the autopilot to enact one of those maneuvers.
Great. For those of you asking, yes, we will share the presentation and recording with you all following the session today. I think that's it for questions right now, Paige. So unless you have something else you'd like to share, I'm happy to wrap things up for us.
No, just thank you very much, everyone, for joining us this afternoon. And by all means, if you want to talk to our engineers, our smart people, then I understand, and please reach out to us to do so. Thank you.
Wonderful. On behalf of AUVSI, I'd like to thank Paige for his presentation and discussion today. Very valuable, a lot of great feedback in the chat and through the Q&A. You are going to receive a link to access the webinar recording within the next week, along with a copy of the slide deck. Another exciting feature is that all of our webinar recordings are now available on AUVSI's learning and engagement platform, Able. When you receive the viewing link, there will be additional information about accessing the recording in Able. We'd like to thank our sponsors, Kongsberg Geospatial, once again for their generous support of today's webinar. Be sure to check back frequently to see future webinar offerings by visiting our website at auvsi.org, events and webinars. If you have additional questions or comments, please email us at education@auvsi.org. Lastly, today's program is copyrighted by AUVSI with all rights reserved. We thank you and we hope you have a great rest of the day.